Hi everyone, these are the notes for section 7.6. Okay, so there's kind of a couple different things going on in this chapter, or this section, but basically it's what can we do with three-dimensional shapes. So one thing we talk about is the cross section. So that's like if you have your three-dimensional shape and you cut it, what shape would appear at the top? Like if you had an orange and you chopped it in half, you'd have a circle at the top. Okay, so that's when we have a plane, so a flat surface, like the knife cutting the circle, and then a solid, or the sphere. So the knife would be the plane, and this orange would be the solid, the sphere. So we're going to talk about what kind of cross-section shapes would have depending on how they're cut. Euler's formula tells us how many faces, vertices, or edges a three-dimensional figure would have given two of those variables. So we're going to be able to find, if we know that it has a certain number of edges and vertices, how many faces that shape would have as well. And then the main idea that we're talking about is similar three-dimensional shapes and how we could find a surface area or a volume given the ratio that exists between them. Okay, so if we have two figures that are similar and we're comparing their sides, okay, so we're comparing their sides A to B, then the ratio of the perimeters is just those numbers, those side lengths. If we wanted to find their areas, ratio of their areas, we would square them, and then their volumes, we would cube them, which makes a lot of sense because if we were finding the perimeter, it would be just like inches or feet, and then their area would be inches squared, and their volume would be inches cubed. So it kind of goes with that. So if you're doing volume, three-dimensional, we cube it. Area is two-dimensional, so we square it. And perimeter is just length, so it stays what it is. Okay, so let's take a look at our examples and try to figure this out. Okay, so our first example, they tell us that the figures are similar, and we're going to compare the first one to the second. And we want to find the ratio of their perimeters and their areas. So if we compare the first to the second and make a ratio with them, we would have 2/4, which is 1/2. So the first to the second, 2/4. So the ratio of their perimeters would be 1/2. So that means that the perimeter of this one is half as big as the perimeter of that one. Okay. So the ratio of their areas is that A over B squared. So 1/2 squared. So that means we square each one. So 1 squared is 1, 2 squared is 4. So that means that the area of this one is going to be 1/4 of the area of this one, or this one's going to be 4 times bigger. And if you think about it, if this was a square, the area of this one would be 4, and the area of this one would be 16. So it is 1/4 of it. So that's all we needed to find, though, the ratio of the perimeters and the ratio of the areas. So in the next problem, we're going to use those ratios to find a missing area. So again, it tells us that the figures are similar and that the area of this small one is 6 inches squared. And we want to find the area of the big one. Okay, so to do that, we have to use the ratio of their areas. So let's find the ratio of their perimeters first, which again would be 1/2, 3/6. So that means that the ratio of their areas would be 1/2 squared again. Okay, so we know that they're similar. So if you think back to chapter 4, all that stuff that was similar, we always made proportions to find the missing value. So that's the same thing we're going to do here. So we know they're similar, and their ratio of their areas is 1/4. So 1/4 equals 6/x. Why did I put the 6 in the top? Good. I hope you said because I put the 1 in the top. The 1 came from the smaller figure. I did small over big. So this is for the small, and then the big we don't know. So small over big, small over big. Okay, and if we cross multiply, we get that x equals 24. So the area would be 24 inches squared. It's kind of like that first one, how I said if you multiply by 4, same thing. But we can do it by finding a proportion. It won't always be as easy as just multiplying by 4. All of them are going to be a different ratio. So let's take a look at the next one. So we want to find the ratio of the perimeters given that they're similar. So this one is kind of completely different. They told us what their surface areas are, but we want to go backwards and find the ratio of their perimeters. So this means we have the ratio of their areas. So we'll do 50 over 128. So I did this one over that one. So we can simplify by reducing by 2. So we have 25 over 64. So the ratio of their areas is 25 over 64. But we want the ratio of their perimeters. So we're going backwards. So instead of raising it to the second power, what are we going to do to find the ratio of the perimeters? Good. The opposite of raising something to the second power would be taking the square root. So if we take the square root, we would have 5 over 8. So the ratio of their perimeters is 5 over 8. Okay, let's move down to the bottom. So it says that the figures are similar. The area of the smaller one is 65 meters squared. Find the area of the large. Okay, so this is just like what we did for this example. So I want you to go ahead and pause your video and figure out the answer to that question. Okay, so we got ratio of perimeters is 13 over 5. So if we squared that, we get 169 over 25. And then we're going to make our proportion, and I put 65 in the bottom since the 25 came from the smaller. So it was big over small for this one. You didn't have to write it that way. You could have had it the other way like we did for the example up at the top. Okay, so we ended up having that the area of the larger figure was 439.4 meters squared. Remember, if you have any questions on how we got that, make sure you write it down to ask next class. Okay, so the next example is very similar to what we just did, except it's talking about volume now. Okay, and they kind of did some funny things with those shapes, so we need to figure out which sides go together. So if we think about this side, that's 6. That is like the height of it if it's standing that way. So what side corresponds to that in the littler shape? Okay, good. That would be this side or one of those sides, because that side is like standing on its skinny side, not on the flat side, the bigger flat side. So those sides go together. Okay, so we need to figure out what goes, if we have ones that have numbers on them that go together. So the 9 is like how far back it goes. So that would correspond to the 6 over here. So those are the two sides that we're going to use to find our ratios. So first, start with the ratio of the perimeters, always. And if we reduce, we get 2/3. So now we want to find the ratio of the volumes, since they were talking about volumes in this problem. So remember, that's the ratio of the perimeters to the third power. So 2 to the third would be 2 times 2 times 2, which is 8. 3 to the third is 27. Okay, so now we write our proportion just like we did for the other ones. So go ahead and pause, set up your proportion, and solve for the volume of the smaller figure. Okay, so here's my proportion. 8 over 27 equals x over 648. So we ended up that the volume of the smaller figure was 192 inches cubed. Okay, so I would like you to pause again and try to find the surface area of the smaller figure for this example. So we found the ratios of the areas, made our proportion, and we ended up that the surface area of the smaller figure is 64 pi yards squared. Okay, so let's talk about these last examples on the right side. So the first top one talks about the cross section. So remember, that's when we have our flat surface intersecting our three-dimensional surface. So if you highlight them, it might help you see like where they cross. So if we have this flat surface intersecting that sphere, kind of like the orange I was talking about, what shape would we make? So that one would be a circle. Okay, so what about the other two? What do you think? So go ahead and try to figure those out. and we'll talk about the answers in class. Okay, and our last two examples at the bottom, it says to find the number of edges when we're given 20 faces and 12 vertices. So that formula, Euler's formula, was faces plus vertices equals edges plus 2. So plug in what we know. Well, we know it has 20 faces, 12 vertices, and then here we would just solve for E. So go ahead and solve that equation and try the last example. Okay, welcome back. So we ended up with 30 edges and then 12 faces. And I know you can see these answers too. So we had a triangle and a rectangle. Okay, so write down any questions you have. We'll talk about them in class tomorrow. Werner out.